pay attention. Let's deal with the design. It's very interesting for the good students. Design is always, you are creating something, you are forming something. So it's normally very, very, very interesting. So let's go for it. You've seen that. I think this is the third time. We did the analysis where we started with the circuit diagram, went this side and told someone what it does. You saw in the analysis, you had the circuit, you have the input equations, so you are looking for the next state of the state table. Design is the opposite. You have a verbal description of the project. From the verbal description of the project, the first thing is to derive the state table or state diagram. They are the same, and this is the most difficult part. You have to interpret the spec and get the state table or state diagram. And this part is the one that is difficult, that can't even be done by a computer. After this, all these others can be computer. Software can give you the circuit. So that is what we want to do, and it is unique. There is no formula for doing it. It's just you have to reason from first principles. So that is why I'm saying pay attention. When I say derive the whatever table, just do it. Okay, so we will look at the steps for design of synchronous finite state machines. The first one, you get the specification of the desired circuit. Normally the question or the problem will give you the specs. Create the state table, create a state diagram from the specification or state table. That is the most difficult task. That is where brain is used. The rest is following procedure. Problem is, if you fail there, everything down there is a 0 or just a 1 minor mark. That is the problem with designing. So you can create a state table from the state diagram or use whichever you want. Perform state minimization, that is optimizing your system. It will be a next topic, optimization. Determine the number of state variables from the number of states. The number of states will give you the number of state variables to power n. You perform state assignment. You can call a state with a letter like A or S state 0. Now you have to give it a binary digital value. Obtain the binary coded state table. You choose the flip-flops to be used and use the excitation table. And then you derive the simplified flip-flop input and output equation. In the analysis, we had the flip-flop input. We are looking for the next state. Here, the state diagram, by the time you have a state diagram, you know the present state, input, and next state. So you are looking at flip-flop inputs. That's the difference. Then you draw your logic diagram. So those are the steps that you do in designing synchronous finite state machines. From now on, we're just going to look at examples. And the first example is the basic that I will go slowly and take as many questions as you will ask. So, step 1, we are going to look at what we call sequence detectors. So, somebody gives you a question. Design a circuit that detects 3 or more consecutive 1 in a string of bits coming through an input line. You've got a serial line coming into your circuit that is clogged. Somebody is busy pumping in bits 0, 1, 0, 1. You want your circuit to detect if 3 or more ones consecutive. The sequence should be 3 or more consecutive ones, not a 0 in between, has come through the input line. You have to understand the problem. Design, you can't design something you don't understand. So understanding the problem, specification. So that is your circuit. X is your input, Z is your output. There are bits coming in serially through here. Z should be asserted, Z should be 1 if 3 or more consecutive ones have come through X. That is what we want to design. You have to understand what you want to design. What type of machine do you want to design? Do you want to design a milli or more? And then I told you the most important thing is to determine the states and draw a state diagram. Or in some cases, like counter, the table is easier than the diagram, or they are all at the same level. So now, I'm giving you, because I won't check, I will use time. I'm giving you 5 minutes. 5 minutes is a bit too much. This is your X. 0 comes in 0, 1, 1, 1. When will Z be 1? So I'm giving you 3 minutes. Can you write this? Can you write this and tell me when Z will be 1? You are understanding the problem. The sequence is coming in. This bit comes in, next that, next that, next. When will be Z be 1? Take your time and do that. I'm giving you 3 minutes. I've done it. You still have 2 more minutes. But if you've done it, there are 2 machines. So you should differentiate which one is milli and which one is more. In my circuit, I've got the same sequence, but for 2 machines. You should use that sequence to differentiate the behavior of a milli and a more machines. People have done it. They've shown me the answer on chart. So there's those ones who said 5 and 6 correct. You've got 0, 0, 1. That is the first one. Second one, third consecutive one, so it changes to 1. Fourth consecutive one, that should be 1. Then goes to 0. It breaks the cycle, so that is 0. 1 is not consecutive 1. So you got that answer. What machine is that? The milli response. Immediately the input changes, it responds. Mfundo, you are right. You will see 1 for the more, and you will see the difference. One is faster than the other. The other one is slower. The milli, immediately the input changes, it reacts to it. The more doesn't. It reacts to the state. Okay, those ones who did the difference is the more circuit will just delay by a circle until the clock happens. So that is the difference between milli and more. Just which one is milli, which one is more. So we've said the more is the same, but they all do the same thing, but it will delay by it will wait for the clock to change. So it will only affect the change in the next clock cycle, whereas the milli just changes there and then. So we have understood what we need to do. The most important thing is, do you know what you should do? We know what we need to do. We know what we need to design. So now let's do it. So the next is to derive the state diagram or state table. And that is the most important thing. What is your state? What should you keep in memory? Somebody to tell me, what should you keep in memory? Remember, the state is the condition at the cues of the flip-flops. That is what is kept in memory. What should we keep in memory? Yes, we've got an answer there. Umeshan input. Okay, let's leave it at that. Another answer. What should you keep in memory? What is the question? You want to know if 3 or more consecutive ones have come in through a line. This is design. So what should you keep in memory? I'm waiting for an answer. Okay. The previous state. And what is the previous state, Sizwe? Okay, Ashlyn. No. We are not talking of the number of states. What is the meaning? What name? What is the meaning of a state here? Abdul, you are correct. The number of ones encountered. That is what your memory should have. Look at how we define. The most important thing in design is, what do you call a state? What past knowledge do you need? So Abdul Khalid is telling us we need the number of ones encountered. Is he right or wrong? Okay, somebody said input. If you keep the input, you wouldn't know whether you have 2 or 3 ones. If you say previous state, we don't know what a state is. We are trying to define a state. If you say 3 states, what is your state? So the right person, the person who has done, say the correct thing is Abdul, you say the number of ones encountered. So that is the most, actually that is the beginning of the question. If you know what a state is, you'll definitely try, you won't fail. So let's look at state 0. Is 0 ones detected? Can you fill in your states? Let's see. Continue from there. Design is you do it. There is nobody who will tell. A state is not always the number of ones. This is based on the question. So you can't memorize that the state is number. If the question changes to 2 or consecutive or 1, 0, the state changes. So you have to reason on the fly, reason based on the question. So can we finish all the states? Ashlyn, you said 3 states or 4. Can you give us, can you say state 0 is this, state 1 is this, state 2 is this? Can you go for it? 2 minutes to do that. We have done the first state. Somebody has said our state is the number of ones encountered. Abdul Khalid said that, you are right. So state 0 is no one encountered. So can you give me the other states? And that is designed for you. 2 minutes. This, I said, is the most difficult part. Try and think. Don't just sit there. I know some of you are in bed. Some of you are where design, you won't survive. You have to think. And the answer changes depending on the question. There is no memory here. I basically don't, in all my courses, I don't even bother that somebody is copying or doing what I'm hearing people actually saying that, oh, the pass rates are high because people are copying, discussing with each other. I'm not worried of that. My pass rate in my section in digital systems was even lower than the normal pass rate. The questions will be customized. You can have your notes, you can have what design is just design. So when I tell you that, we've said there was, Abdul told us that a state, we must keep the number of ones encountered. That is what our memory should have. So the first state 0, I've told you that from what he said, we have not encountered the first one. So what should state 1 be, state 2 be, state 3 until that? Mikash, we have already, on our slides there, it says state 0 is 0 ones detected. So continue from there, Mikash Mudai, continue. And tell me how many states should you keep? Minendle, if you say 1 detected, which state is that? Give them numbers. I want to know how many you will have. Okay. Minendle, state 1 is 1 detected. Continue. You are on the right track. This is reasoning. You need. So continue, guys. We are doing a design. We will come up with the circuit. Okay, Minendle, I'm watching. You are on the right track. I want to see where you will stop. Sizwe. Okay, Sizwe, you are okay, correct? Okay, more people, yes? And this is, to me, if a student gets this part correct, Unfortunately for you, I'm the one who is marking, so it is for you as well. If you can get this in the diagram correct, I will give you more than half the marks. To me, you've solved the problem. So this is what we should have. State 1 is 1 detected. State 2 is 2 ones detected. State 3 is the third consecutive one detected, and the output should be 1. There are those people who would have state 4 and still have the right answer. Are you getting that? That is why we've got optimization of state reduction. I said separate chapters. So don't worry if you had more, but you don't need to have 2 more states. Any question up to there? Now, can you draw the state diagrams for both the milli and the mo machine? You need to also understand the configuration of the state diagram. Can you just draw it? I'm giving you 3 minutes. You have to know how the input is, where the output is for both those. Try and draw it. I'm giving you 3 minutes. I will deal with the question. Sanelisiwe, we started from the question and said we want to identify 3 or more consecutive ones. And then we asked, what should we keep in memory? What you keep in memory, in mind. Let me go back to our remote with up and down buttons. What do you keep in mind? What does the decoder or whatever keep in mind? It keeps in mind the position it is in. Am I on channel 200? When you press up, it goes to 201. When you press down, it goes to 199. So what you keep in state is what you want in memory. So one person told us that we should keep in mind the number of ones detected. That person said that is what you need in memory. That is when we knew the meaning of our state. Then we say the first state is you have not detected anyone. The second state is you have detected the first one. The third, you have detected the second one. And then the fourth is you have detected the third one and your output should be 1. That is what we said. Are you okay, Sanelisi SBC? Okay, Sahil? No. Sahil, Lalji, that is what I'm saying. Design. If I change this question, these are sequence detectors. Each question is different. If you design a flip-flop, design what? Each question is different. The procedure of deriving the state diagram is the same or what, but the states are not the same. Each question is handled different. So to determine the states, you look at the question. It's not unique. We will see other examples, don't worry. So have you guys finished? At least finish a milli state diagram. And if you have finished, please just indicate there that I've finished so that I will look at it and see if my timing is okay. Just say you finished for the milli, and then the more you will do it on your own. Okay, somebody has finished for the milli. Which is a better type of machine to design? That's a good question. There are some cases where you can design both machines. So the one that gives you the easiest state diagram is the one that you design. Okay, we've just seen from the first example that a Mo machine is slower than a milli machine. So if you want speed, you need to design a milli machine. Okay, Umeshan, I'm trying to answer your question, which machine is better? You look at the advantages and they all do the same thing, but you look at the advantages and disadvantages. We've said that from our example, the Mo machine is slower. So if you needed speed, use the milli machine. Now, we have seen that the problem with the milling machine is stability. When the input is changing, already the output is changing. It doesn't wait for the clock. So if you want stable circuits, then use more. So immersion, I'm answering your question by saying it depends on which one you want, which parameter you want in your design. Another thing is the milling machine, we will see this later, always has shorter state diagrams. Okay, the importance of state diagrams, if you have two states, you will use one flip-flop. Okay, if you have 4 states, you will use 2. If you have 5 states, you will use 3. So you will find that a milli can give you 4 states and a more gives you what? 5 states. Then you will have to use more flip-flops in a more, that's making it more expensive. So that is how you look at it to measure. So a milli tends to be cheaper because it always has less states than a more, but it's very unstable. The more is stable and slower. So depends on the design parameter that you want. Okay, so people have finished that. So you should have that. State 0 here, there is what? No one detected. If it keeps on 0, you will circle here. This is the first one you've detected. You go to state 1. If a 0 comes, you go back to square 1. Your cycle is broken. If a 1 comes, you've detected the second one. If a 0 comes, the cycle is broken, you go back to square 1. If a 1 comes, that will be your third one, so the output should be 1. If 1 keeps coming, you remain here is the other consecutive. Remember, we said 3 or consecutive ones. You keep on looping there. But if a 0 comes, you break the cycle and go to your reset or waiting for. This is waiting for the first one. Somebody can say state 0 is 0 once detected. Another one can write state 0 is waiting for the first one. And you say first one has arrived here. Second one has arrived, third one has arrived. The wording can be different, but the same thing. Any question there? I'm taking time because that is the most tricky part. Okay, you are not seeing my video. What I said is S0, you are waiting for the first one. If the first one does not arrive, if a 0 arrives here, you keep on there, the output is 0. If a 1 arrives, is the first one, the output is still 0. The second one arrives, you go there, the output is still 0. If the cycle breaks anywhere here and there, you go back to 0. If it breaks here, you go back to the first state. If a 1 arrives, the third one. If ones keep on arriving while you are there, they are consecutive 1. The question was 3 or more consecutive ones. A 0 arrives, you break the cycle and go stay. That is how that is. Okay, I'm taking questions. That is Millie. If we have to take the yes, 5 ones, we would have 4. It's always more. We would have more states. Remember, the first state is not detected anything. Ashley, we would have more states.
So could we ever have a question where we have to detect the zeros rather than the ones?
Yes. Questions here, design, any question can come from any direction. That is why you have to watch out. You can detect 2, you can detect a 1 and a 0 and a 1, 2 zeros and all that. So that is why you can't memorize the state diagram. You have to reason, and you can't just read it. You have to go through. The best rule of the thumb is go for what you want. I will look at a 1, and finish with what I want. And then I fill in the breakages, the break of the sequence. That is what most people do. Any questions? I'm taking questions there. It's the most important part. There is the Moore circuit. There is a 0. If a 0 it comes, it means my first one has not come. That is, my first one has come. My second one has come. My third one has come. So that is 1. If ones keep on coming, I'm here. If a 0 comes, I go back here. If it breaks here, I go back here. If it breaks here, I go back there. Any question? To me, once you do that, you've passed the question. If you get this correct, I give half marks. The rest is just something long, but it's procedure. From here, you can even use a software to design this. I'm taking questions, yes? Okay, the more is the same as the milli. Remember, our state 0 means you haven't received the first one. State 1, you have received the first one. State 2, you have received the first one. State 1, you have received the first one. State 2, you have received the second one. State 3, you have received the third one. So the output should be 1. If you continue receiving ones, you remain here, consecutive ones. That is our right sequence. Remember, rule of the thumb, start with the right sequence and fill in the gaps. Now, if you receive the first one and you receive a 0, the cycle is broken. You go back to reset or first state. If you receive that, and the cycle is broken, you go back there. If you receive the third one, you will be 1. But if the next is a 0, you go back there. So that is the more. The outputs are on the states and not on the inputs. That is the difference between more and, yes, more and that. Okay. This, it doesn't necessarily mean that the more has more states. It's just in some specific circumstances. You have to check. In this case, they've got equal number of states. But in most cases, the milli always has less. The difference in this, more and milli, is one affects the change after the clock, the other one before, but it's not necessarily that it must have more states. It's not compulsory. In this case, they've got the same states. And please don't even be scared to ask a question. I'm getting questions from chats before. So once you do that, to me, you've done what is required. Okay, now the next is procedure. They are very good people. There are people who know how to follow procedure. But unfortunately for this, if you don't get right here, you are solving a wrong question. You've been told to design something and you end up designing a bomb. So you are wrong. So now, any problem here before we move? Remember step 2, deriving the state diagram. Anybody with a problem?
Sorry, sir.
Yes?
Okay, on the Moore machine, we said the transition from, let's say, from 0 to 1, when the output have to change from 0 to 1, there's a delay.
Yes.
Okay, so from stage 0 to...
There is really no delay. It happens when at the clock, when in the next clock cycle.
Oh, okay. Thank you, sir.
It happens in the next clock cycle, not immediately. The input changes. I'm taking questions. This is our first example, and you have to learn as much as possible. If you have any doubt anywhere, just ask your question. Okay, that was the most important step. If you have, okay, now, let me do that. Let's say we are designing the Moore. Can you check that? And I'm taking questions. We had that. We've moved with that. That was our diagram. And now that is the state diagram. Now we change it to the state table. Anybody who has a problem with that, we know where this one came from. We know the more. So now I put it in a table, same information, different way. I'm taking questions. Here is the present state input, next state output. Present state here is S0. If 1 comes, it will go to S1, the output will be 0. In S0, the input, the output is 0. So this table and these ones are the same. I'm taking questions. Look at this row. If you are in S0 and the input is 0, you remain in S0, the output is 0. If you are in S0 and the input is that 0, you remain in S0 and the output is 0. So that row is what we have described. So you derive your state table. Any question or we move on? They have the same information, it's just a different configuration. Okay, now after the state table, step 4 says perform state minimization. That is optimization, making your machine smaller or cheaper. That will be a next topic. We are not dealing with that. Step 5 says determine the number of state variables. You've got how many states? 1, 2, 3, 4. State variables or flip-flops. How many do you need to have 4 states in binary? So from that, you'll find that you need how many? 2. 2 to the power of state variables should be greater or equal to the number of states. So 2 state variables are necessary, 2 flip-flops are necessary to implement that. Each variable will represent a flip-flop. You have determined that. Now, remember, we are moving with this. I've just separated them. Where did you get 2 tables? Okay, a present state input, next state output. That is what we came with from there. Now, you do what we call a state assignment. You assign binary codes to your states. Remember, you are using 2 flip-flops. So what do? I call state 0, 0, 0. That is state mapping. And there's a way you can map things to reduce the cost of your machine is a subject of a later topic. But for now, let's call S0, 0, 0, S1, 0, 1, S2, 1, 0, S3, 1, 1. So this will be 0, 0, 0, 0. There is your 0, 0 here, 0, 0. This and that remain. Let me take this. S2 is 1, 0. That is why you have 1, 0 here. S0 is 0, 0. That is why you have that. So I've done a binary assignment. Any question? Remember, I said the next is to follow procedure. Okay? Now, the next is to split these to our 2 flip-flops. Okay? So, we are going to our 2 flip-flops. Remember here, we are now working, we are splitting this, making this A, B, next state of A, next state of B. That is, we are splitting this column into 2, that one into 2, basically. That is what we do, yes? Ashlyn, I said there is a way of coming up with the binary assignment. We will look at it later. But if you have 2 things, you can call one if you have 2 states, you don't need any assignment. One will be 0, another one will be 1. If you have 4 states in binary, obviously the only combinations you have are 0, 0, 0, 1, 1. So those are all the combinations for 4 states. So there are different ways, but these are the common ways of mapping. We will look at different ways of mapping to reduce your machine. But for now, if you have 4 states, you can represent them by two binary variables, and those two binary variables can take 0001, 1011. State 0, which is almost the reset state, it's always good to call it 00, but we'll look at the rules of assigning later. That is what we call state assignment. Detailed assignment rules will be done in a later chapter. I did mention that, it's clearly there. For now, let's use this detailed assignment rules is a later topic. Okay, so we have that, we split that. Now we split the tables into present state A, B, X, and next state of A. Remember, the next state of A is a function of the present state of both flip-flops, not just one. B is also there, and the input. Then flip-flop 2 is the B. Flip-flop 1 is the A, which is a function of A, B, X. In the next state, we have split that, and then we have also split the output. The output is a function of A, B, and X. Any question on how we arrived there? Any question? Okay. After splitting that, what do we do? Remember, before I go there, in analysis, you had A, B, X, combinations of present state, and your equations gave you the flip-flop input equations. You used a table to get the next state. Design is the opposite. You've got the present state. From your state diagram, you've got the next state. So you need to decide which flip-flop you will use and use a table to give you the inputs of that flip-flop that will give you that movement from A to AT plus 1. It's the opposite. The table that you use is the excitation table. It's the same as the truth table, the one we were using. So this one tells you if the present state is 0 and the next state is 0, for a D flip-flop, D should be 0. J should be 0, K should be don't care. T flip-flop, T should be 0, set reset, S should be 0, XR. That is the table you use. If you check, it's just the opposite of the truth table. So let's employ that table only on the flip-flops. We are you have to choose the flip-flop you are using. We've got the present state here, present state of B. We know where we came from that, the input of X, the next state, we've got that, and say we are designing that circuit with D. So that will be DA, flip-flop A. We are looking at the input there. And this one is same. Present state AB, input, the next state of flip-flop B. We are using DB. Now, the question we ask is, for a D flip-flop, if the present state is 0 and the next state is 0, what should be at D? The excitation table gives you that, and it is here, but it's common sense. What is at D is the next state. What is at D here is what is at B. Can you fill in that? 2 minutes. You've got the present state, next state. What input should be at D to give you the next state from the present state? So can you just quickly do that? As you do that, if anyone has a question, please ask. So fill in the value for D. DA and DB there. Should be pretty easy and straightforward. 3 minutes. Minendle, correct. That is for a D flip-flop. Actually, the D flip-flop, the input doesn't care. If you have the next state, it's the input. So if you are using a laptop, you should just cut and paste from somewhere. That is, I'm answering Minendle who has asked. So if the next state is 0, then the input at that should also be 0. What is at D becomes the next state. Okay, anyone who has finished? Anybody who has finished filling it in? Okay, I will wait for the first people to finish. Okay, Sahil, you are done. Let me wait for some few other people. Yeah, Ashlyn, yes. That is why I said, no, is the next state that follows D. So you cut and paste from next state, then you have the input that should, remember we are looking at the inputs to the D flip-flops which generate the desired transition. You've got the transition. So what input will make that transition happen? So it is the next state. Okay, so people are done. So now we've got that. So that is why we are saying D is just the same as the next flip. We are designing using a D flip-flop. So that column is just the same as that. Basically, we have finished our design. We have finished what we are doing in this course. The next is what you have. Now, can you give me DA? Remember, we are looking for the equation. In the analysis, we had the equation, we are looking for the next state. Now, we were looking for that. Now, can we get the equation of DA in terms of A, B, and X? Not next state, it's normally not, it's DA that gives the next state. So can we get the equation for DA and then DB? Those ones who have finished, you've got that. I need those two equations. And you should know from the equation gives us a diagram. I want the equation for DA, DB, and Y. Okay, Y is not there. So try and give me that equation. If you've forgotten that from Elec Inch, you need to revise and remind yourself. Once you've gotten the equation for DA, DB, you can show me. And then I will wait for some few people before we move to another step. I'm taking most of my time in this lecture to do one example, because from now on we'll just be doing examples. So the first example gives us the procedure. We are laying down the procedure with the first example. Okay, if you've got the equation for DA and DB, please, can you just let me know? Okay, that's fine. Minendle, that is okay. DB. Now, once you get those equations, that equation is already a circuit. Yeah, somebody has gone, Minendle, Yashil has gone further. Your answer is correct, Minendle, but now you need to minimize your circuit. So Yashil Mora has gone further and use the equations, Boolean equations, or use the K-map to simplify your equation. And that is how we are supposed to be going. I'm waiting for some few people to give me the equation for DA. Please, you've got notes for this, but forget about notes. If you read them, just leave. Let's flow with the lecture. Okay, now, from then on, you've got a circuit. In fact, if you don't have time in an exam, you can stop there. You won't lose a lot. Now, from this stage is minimization. Now, Y also, you've got all that, the output. Y is also given by that. You had that. So you've got the table for A, B, X, and Y from the main table. So that is the equation of Y. Now, you've got the circuit. If you implement that circuit, it will do what you want, but it's an expensive circuit. So what next is now to perform the minimization of the circuit. And that is not the subject of today. So you can use scan of maps, or you can use the equations. So you have A, B, X for flip-flop A there. You put your Karnaugh maps, min term, max terms, you will get that. Somebody called A or BX. Somebody got that already. Then you've got your DB is that, and then you've got your Y is given by that. Now, can you draw the circuit? Just draw the circuit that you have designed up to there. You know, you've got 2D flip-flops. You know what we mean when we say A. Just draw the circuit and see how it looks like. That is the circuit you've designed. From the equations, of course, you know the equations, you can draw the circuit. So I'm giving you 2 minutes to draw the circuit. If you finish, just send me a chat and say you that. I will repeat that. There was no volume. I'll repeat that. It was in mute. He asked, we've got 2 equations. Let me start with the flip-flop 1A. dA is the equation we came with. Is the equation we came with from here. So that's the equation we came with. We need to minimize that equation. There are 2 ways. You can use the Boolean equations, or you can use the K-map. People prefer tables than mathematics, and yet they're supposed to be engineers, okay? So if we use a table, dA, you've got A, B, and X. So the first term, max term, dA will be 1 where A is 0, B is 1, X is 1. A is 0, B is 1, X is 1. So that is 1. It will also be 1 where A is 1, B is 0, X is 1. 1, 0, 1. That is that. It will be 1 where A is 1, B is 1, X is 1. 1, 1, 1 there. Then from there you close this and close that. Then you get dA is what? A plus BX. AX plus BX. You will get that. We came with this, you plotted it into the K-map, you minimize it, you get that. You came with this, plot it here, close it like that, you get AB. So you have those equations. This is the first equation, this is the minimized, first minimized. Now the question is, have you drawn the circuit? If you finish drawing the circuit, let me know. Don't draw a need circuit, just scribble something there and get the functionality. Nobody marks you for being what, an artist or something. Just draw something and let's move. I just want you to have a feel of drawing the final circuit. Okay, Sanelisi, you've done. Done. Jambulo done. I'm waiting for 2, 3 more. Yashil done. So that is the circuit that you've been doing. Nokolo done, Caesar done. Okay. So that is the circuit that you've been designing. Those are your equations, those are your final equations, and that is the circuit that you designed. Any question? All that work you've been doing, you've designed that circuit as a finite state without knowing what you are designing. As a finite state machine, you've got your X, these are your S and your B's, and those are your connections. You should have gotten that circuit. There is your Y. Y is AB. So A comes here to Y, and B comes back here to Y. That's the circuit you designed. Analysis was the opposite. If you analyze, you should get the state diagram. Any question? Now, this one says implement The next thing you need to do is to implement what? The milli one. On your own, go through the same and implement the millisecond. I don't have an answer for that. I did the more. Okay, we still have 20 minutes. Any question up to there? I said we've taken most of our lecture on this question because it's the first one. We needed to lay down the procedure. Next, we are just going to deal with examples this week and next week. Okay, now, example 2. I'm just interested in the state diagram. After that, the procedure is the same. What type of machine is that? Determine the states and draw a state diagram. You can draw both milli and more. So for those who have finished, you must tell me the meaning of your state. Most of you have told me. State 0 is 0 detected. State 1 is 1 detected. Those ones who are struggling, you've been given the meaning of the states. Can you finish the state diagram? Yeah, it is a milli machine. Okay, finish the state diagram. A man is a milli machine. When immediately the input is changes, it also changes. Yes. Okay, people are done with the diagram. Those ones who are done, you should have gotten something like that. 2 states. I told you the easiest way. The first thing, these are what we call sequence recognizers. It's a group of machines that recognize. Sequence recognizers go for the right thing. Say 0 detected 1, you go 1, that is 1 detected. That is the right combination you need. And then fill in the dots. If you are here and the one, yes?
So this particular problem, it's not possible to get 2 consecutive ones at the output.
No, the question does not tell you that. You have bits coming. You are adding on the question. The question just tells you that you've got bits coming. They can 1 0 1 1 1. You just want when 0 1 comes, a 1. It did not say 0 1 1. Are you getting the question? The question did not say 0 1 1.
Okay.
Just 0 1. Just recognizing a sequence 0 1. Are we okay there?
Yes, sir, I
So
understand now.
So what you are saying, look here, if you have a 0, a 1 comes here. Are you watching? There is a 1. The next one comes, the output should be 0. That is what you are asking. Consecutive ones should be 0. The question doesn't want you to identify 0, 1 and consecutive. It just wants 0, 1 only. So as I said, go for the right one. That is 0. That is 1. 1 goes there. So when 1 comes, you are not interested in this, but the 1 has come anyway. When a 0 comes, you break the cycle, go there. 0, you remain there. So that is easy. Try and do a more and see if it will be easy to get. Now, our time is almost up. We didn't have a break. Now, from now here, I'm not going to be taking time talking about how to convert this to that. You should know. You've got your present state input, next state output. From there to there, by now you should know. I shouldn't waste time. Assignment, I've got 2 states. How many variables do I need? I need 1. How many flip-flops? I need 1. So remember, I'm implementing using a JS. Wait, I'm just, yes. Jabulo, the circle on state 2 with a 1 as input. I don't understand. The state 2 is the one we are calling S1. This is a 0 detected. This is a 1 detected. Look at how we are calling states Njabulu. This is a 0 detected. If you detect a 0, you are here. If you detect a 1, you go here. If you detect a 1, you remain here. If you detect a 0, you go here. Let's finish with that. Are you getting that? When should the output be a 1? The output should be 1 when you detected a 0, and you are here when you detected a 0, and the 1 comes. So that is where your output is. If you detect another 1, it will be a consecutive 1. You will still have a 1, but the output will be 0. The circle will have been broken. So just go through that. Okay? Now, yes, another question. Design is very interesting. Yes? Another, okay. It's an okay. Okay? Design is very interesting and ask. So, we said there are 2 states. 2 states, you will only need 1 flip-flop. 2 to the power of n. So, for 1 flip-flop, state 0, you call it 0. State 1, you call it 1. So, how did we get that? This is state 0. State 0, we called it 0. That was state 0. State 1, we called it 1. That is the next state. Then you've got your Y. Remember, we are looking for the inputs. Now here, what J, we are designing using a JK flip-flop. So we say, if the present state is 0 and the next state is 0, what should we have at J? What should we have at K? We come to that table. This table is given, but you can infer it. If the present state is 0 and the next state is 0, J should be 0, K is don't care. So we should have a 0 here and a don't care there. That is how we determine that from that excitation table. Taking questions. If the present state is 0 and the next state is 1, what should be at JK to cause that transition? You say 0, 1, J should be 1, K should be X. 1, don't care. So fill that one in from that table. Then after that, you get your equations for J. You should know how to get your equations. You get your equation for K. You get your equation for Y. Y, we already had it from the diagram. Then after that, you minimize. This is actually the right answer. It's just that it's an expensive circuit. If you are running short of time in the exam, you stop here. You can even tell me that is left is minimization, but that is also an answer. To me, if you get the state diagram, you know what you are doing. Okay, so that is K map, and then you should get. So you are seeing how we are going to go. I'm not going to be telling you how you feel in this. You will do them at home. Once you minimize that, that is what you have. And then after that, that is your circuit. If you are running short of time, don't even waste time drawing that circuit. If you have this, you've got that. In fact, these days, I don't even ask you to draw the circuit. I just tell you to stop there. So that is the second example in design. We have exhausted our time. We didn't have a break. So I'm taking questions. If there are no questions, the whole of next week, we're still looking at this design and looking at examples and a tutorial. After that, we need to have the first assessment. Class rep, you will tell me when you need the first assessment. Otherwise, I'm taking questions. Make sure you mark the register. Don't forget. I've opened it for 30 more minutes for people to log there and mark it. Anybody with a question? So after analysis and design, we will have our first assessment that covers this part.